Well, hello everybody, and welcome to this webinar on antenna group delay. I'm Jeff Barney, XF's product manager, and I'll be presenting this today. The webinar, as you can see, this is more of a market research webinar as opposed to maybe what you're more familiar with in terms of a promotional webinar. This came about because we were approached by a customer at the beginning of the year, just asking us what we can do for antenna group delay. And so we investigated a little bit, came up with a new type of metric using the XF tool. Went back and forth with them, got good feedback. We also opened it up to, or talked to another smaller select list of customers. Again, got good feedback. And so now we're just wanting to open it up to a broader audience. Group delay is not new for Remcom, but we had to rethink it whenever we were thinking about antenna group delay. And so we're just wanting to get feedback, from users and people that are out in industry who may have, more experience with this or may be using it in your job, daily. And so we're just, looking to get some feedback. So I go to the next slide. Content, in terms of the agenda, it's going to be pretty simple. We're going to talk about antenna group delay, the traditional 2-port metric, and then the newer metric that we came up with. And then also as part of our investigation, we came across an antenna fidelity factor. And so that's another type of output that we'll go over quickly at the end. If you have questions at any point in time, feel free to go ahead and answer them. At the end, I'll pause, I'll see what questions came in. If there's anything I'm comfortable answering, well, then I'll go ahead and answer those at the end. So where's my pointer? So let's go ahead and get started. Oh, I'll also say that this is probably going to take me about 25 minutes to run through, and then there'll be questions at the end. So for starters, group delay, thinking about a traditional 2-port group delay, it's defined as the rate of change of transmission phase angle with respect to frequency. And here's the corresponding equation. Pretty straightforward. And I guess as I looked at this, this definition doesn't, it just restates the equation. It doesn't really give me too much information on what it actually means. So if we do a little bit more digging, we found some other information here that says antenna group delay is a measure of phase distortion. So that certainly sounds relevant for antenna designers. Phase distortion sounds like a bad thing. I guess thinking about some of the advancements or the increased usage of ultra wideband applications, there's wider channels, and therefore you need to be paying attention to group delay over that entire channel. Whereas before, this metric wasn't as of much interest. If you were just thinking of Wi-Fi at 2.4 gigahertz, it's a narrow channel, it's minimal phase distortion across that channel. And so this would explain at least why it's, antenna group delay is becoming more prevalent in wider band applications. So if we go on, we can say that antenna group delay, or just group delay in general, is the actual transit time of a signal through a device under test as a function of frequency. So this, I guess, makes the most sense to me intuitively to understand. Think of like a 2-port device, a filter, for example. If we look at, as I mentioned, like group delay is a result that XF has had for 15, 20 years. The group delay itself is not new to us, and so we have group delay as a result that's available in XF. And if we think about the transit time of the signal through the device versus frequency, so if we're sending a 6 gigahertz signal through the device, we can see that it's going to take roughly 6.755 nanoseconds to get to port 2 from port 1. If we increase frequency, up around 7 and 7.75 gigahertz, well, we can see that transit time decreases and it gets to the second port faster. And so if we were thinking about a distortionless device, well, this would be a flat line, the whole way across, because it takes the same amount of time for signals to travel, and therefore there's no distortion. So that's kind of, I guess, how at least that's kind of what group delay means, or how we're thinking about it. And then we found some other information down here that group delay variation of 100 or 150 picoseconds is considered acceptable for ultra wideband applications. So if we take the variation over this, what is the slowest signal versus what is the fastest signal? What's the delta in between? That delta should be 100 or 150 picoseconds for ultra wideband applications. So this is, everything on this slide is just a traditional two-port group delay metric and interpretation. We then needed to take that and expand on it and say, well, okay, if we're looking at antenna group delay, how do you get the group delay for just an antenna? Thinking about it from a measurement standpoint, if we're connecting this to a VNA, we have a transmit antenna, a receive antenna, and you can calculate group delay between those two antennas with your VNA. From a component level, on a transmit side, you have your mixer, your power amplifier, your matching network, the actual antenna itself. There's the propagation channel, the time of flight, which is going to increase that transit time. And then on the receiver side, you have similar components. And so if you're interested in just designing your antenna, what is the group delay of your antenna, the matching network and the transmit antenna, that's going to be kind of tricky to figure out given a VNA measurement, because all of this information, or at least most of this information from port 1 to port 2 is captured. And so how do you go about figuring out just what the impact of your antenna is? So some ways we can look at that is the group delay of the antenna is calculated approximately by taking the frequency derivative of the input impedance phase function. So this seems like a pretty straightforward measurement to take. Look at S11, look at the input impedance, and based on the frequency derivative, you can get at least an approximation of your group delay looking into the port of your antenna. In actuality, group delay of an antenna is composed of contribution from two constituents. You've got your input impedance and you have your far field phase. And so what we've developed here at Remcom, and this may be familiar to all of you, but we have an antenna group delay metric where we're looking at what is our input measured at our voltage source going into the matching network or into the transmit antenna, and then what is our output measured over here coming out of the or incorporating the input impedance as well as the far field phase. And so this is something that we're able to do from a simulation perspective because we can isolate the antenna directly and analyze the antenna directly, and we can remove the channel, the time of flight, and we can also remove the receive antenna because we don't need those from a simulation perspective. So this is the new result, at least for Remcom, that we're looking at and we're wanting to analyze and get your feedback on. So I've got an example or two here that I want to go over. The first one is an antenna from MVG. This is their WD6000. It's designed to operate from 6 to 10 gigahertz. The input impedance and the far zone patterns are stable, making it an excellent ultra wideband antenna. So if we look at S11, over 6 to 10 gigahertz, we can see a nice match below 10 dB. If we look at the input impedance, we can see that this I say is relative. I'm not sure how to describe this. Is it relatively stable? Is it not changing very much? But it's well behaved, I guess. I don't know. But anyways, this is the input impedance. And if we look at the far zone radiation patterns, it's pretty stable. 6, 8, 10 gigahertz. We're getting the traditional dipole radiation pattern, and there's not much variation. So we started out by just running a simulation just to kind of familiarize ourselves with what we already know from a measurement perspective. So we took 2 of these antennas, we put them into a single XFdtd simulation space. We separated them by 2 meters, and there's a port on the transmitter, a port on the receiver, and we can use the traditional group delay metric that's available in XF for that 2-port definition. And so this is the group delay that we measured versus frequency, just as like, getting a baseline. And then we moved on to, well, all right, if we just wanted to look at group delay for a single antenna, well, then let's do a comparison there. And so here, the graph on the left is based on this 2-port antenna separated 2 meters. The graph on the right is using the antenna group delay metric, that's new that we outlined. The first thing that you might note, is the difference between 6 nanoseconds versus 3 nanoseconds. So we're going to ignore that DC offset just because, the propagation distance or the flight time, between these 2 antennas is going to be factored in. So we can go ahead and ignore that. And primarily what we're interested in instead is the variation, from the maximum to the minimum. In this case on the left, we have 2 antennas. So we'll take this variation, divide it by 2, and that gives us roughly 16.5 picoseconds. And then if we do the same thing on the right, we can take the maximum and the minimum, just subtract them directly because there's only a single antenna, and that gives us 21 picoseconds. One thing to note is that when we're looking at antenna group delay, we can do it based on polarization. So in this case, the antenna was primarily theta polarized. So that's the data here that we were looking at. We could also look at phi polarization if we had wanted. And when we look at these numbers, we're in the same ballpark. We're not going to say that the graph on the left is truth. There's 2 antennas, there's transit time, there's multiple other factors that go into this. So just from the standpoint, we're in the same ballpark, 16 picoseconds versus 21 picoseconds. We consider it to be acceptable in terms of being comfortable that this new metric that we came up with, is valid or has some validity associated with it. If we then move on, we mentioned that group delay is a function of the far zone far field phase pattern. And so instead of just looking at the single point directly between the antennas, we're able to look at a couple of cut planes around the antenna. So here we've set up 2 planes for an observation angle. We have the H plane as well as the E plane. And if we pick just the point in the middle, so on the XY axis, theta equals 90 degrees, phi equals 0 degrees, we can take that data, and this gives us the antenna group delay that we looked at before. This is antenna group delay versus frequency. We can take the maximum value, the minimum value, it comes out to roughly 21 picoseconds. So this is the single data point for that observation angle. We can get the same, or we can go through the same process and get a single data point for all of these observation angles in the H plane as well as the E plane. We could plot those directly if we wanted, or instead we created a CDF of this, so a cumulative distribution function, just showing more of a statistical perspective of how does the group delay vary over the 2 planes. And so here where they intersect, that's the single point that is on both the E plane and the H plane, around 21 picoseconds. In terms of interpreting this, if we think about the H plane, it's around the azimuth angle of essentially the dipole pattern, and so we wouldn't expect very much variation in the H plane, and we're seeing that here in the graph. Roughly it's 21 picoseconds. It's a vertical line. It doesn't matter which point on that plane we are at, we're getting the same 21 picosecond variation. If we look at the E plane has more variability in it. We're moving up and down closer to the poles, and the variation in group delay moves around, right? So sometimes it gets a little bit better. The variation decreases less than 10 picoseconds, and in a worst case, the variation for a single point would be around 28 or 29 picoseconds. So this is some way of looking at the data. If you wanted to make this a patch or the full 3D pattern or the upper hemisphere, you can pick whatever observation angles that you want. You can look at the points individually, or you can look at the CDF to see how your antenna is performing. I want to break from the slides here briefly just to bring up the XF application and show you how we're doing this from a project setup XF standpoint. For those of you that have not seen XF before, this is the user interface. On the left-hand side, we have the project tree. In this case, we have a CAD model of the antenna imported. We also have a circuit component defined here across the middle of the antenna. So this is our single port that we're using as an excitation. We also have several far zone sensors. These far zone sensors are used, in terms of defining the observation angles where we want to collect group delay. Materials, the waveform. The waveform that we're using here is a modulated Gaussian. So this is, XF is a time domain solver, and so we can put in time domain waveforms. And with a single waveform, we can cover the entire frequency range from 6 to 10 gigahertz in a single simulation. And we can run that simulation, and then we can get results. And in this case, let's just look at the antenna in free space. Let's just grab one of these far zone sensors just so we can look at the observation points. We'll just look at the gain result. The result down here doesn't really matter which ones we select. And then, because this is, I guess, a newer feature, the post-processing that we do is available through scripting. So this is a custom XF script that we have written that pulls the necessary data from the simulation, calculates the antenna group delay, and then plots it. So we have that script. You can import scripts down here in the scripting menu, or in the scripting portion of the project, but alternatively we have a macros menu. And so this is just available for all of our projects. So antenna group delay. I run that script. It's going to ask me which polarization I want to calculate group delay for. It's theta. I click OK. The macro runs for a second, and we get the group delay result down here at the bottom. So if you wanted to look at a different plane or a different set of observation angles, you can do that. You can rerun the script. If you were looking at just a single point and you run the script, oh, let me select my gain result. Now let me run the script. Well, then this will give you the group delay versus frequency. So if I open up both of these graphs, the first graph I had selected the E plane, and so this gave me the CDF over that E plane. The second time I selected a single point. And if you select a single point, well, then you get the group delay versus frequency. So that's, I guess, basically how it's implemented in XF and how you can access this data through XF and through the user interface and through the script that we wrote for post-processing. Coming back to the slide deck, just a couple other examples. This one here, we're going to say, well, what if we take our antenna, instead of it being in free space, what if we put a lossless dielectric sheet near the antenna? This is going to be a proxy for a radome. We're going to expect the group delay to decrease, or we're going to expect the variation to increase. And that's what we're seeing here, right? So these two graphs on the left were the free space. You add the dielectric sheet, and those graphs move to the right, and your group delay variation is going to increase, or your distortion is going to increase. Worst case, it's still below 100 picoseconds, but this is what we can see in the E plane and the H plane. Moving on and looking at a second example, this time we're going to look at a dual cavity antenna. This has poor ultra wideband performance, at least from a group delay perspective. There's a cavity on top, a cavity on the bottom, and you can't really see it, but there's a feed right here that is connecting the top conductor down to the middle conductor. If we look at the impedance versus frequency, in this case, we're looking at 5 to 6 gigahertz is the operational bandwidth. And this is kind of like a good or a typical impedance that you would see for this type of antenna. and the corresponding S parameters look good as well. You'll notice there is a lot of variation though in the impedance, and also when we then look at the radiation pattern from 5 to 5.5 to 6 gigahertz, that radiation pattern moves around quite a bit as well. So thinking about the first antenna, the impedance was didn't have this level of variability, and the far zone patterns were very stable. This antenna moves around quite a bit, and in that case, the group delay is significantly worse, right? We're looking at 2 to 8 nanoseconds of variation. So this would not be a good antenna design from an antenna group delay perspective. And that covers what I wanted to go over in terms of group delay. If we then move on to a second metric, which is an antenna fidelity factor. This is similar to group delay in that it's a metric of how much distortion is introduced. But in this case, we're looking at an input signal traveling through the device, and then we're looking at the output signal, and we're using a cross correlation to figure out how much correlation there is between the input signal and the output signal. So if we consider the black waveform here to be the input signal, we look at the red signal as being the output signal. And as we move the signal across, like right now, there's no correlation, that there's no overlap. But as we move that signal across, well, then we start to see, there's some correlation there. And as we continue to move the signal farther, we can get another correlation metric. And in this case, we're about reaching peak correlation, or the maximum correlation between the two signals. And then, we continue moving it on until there's no correlation again. I also wanted to mention here that, like we have to factor in or normalize the received signal magnitude, as it propagates, the output signal is going to be significantly weaker than the input signal. And so we need to account for that as part of this cross correlation calculation. But given that kind of methodology, we can go back and look at the WD 6000. This is the green is the input signal, the red is the output signal. If we look at the autocorrelation on the input signal, so basically, the input signal correlated with itself, we're going to see a correlation of 1. The signal is identical, that's what we would expect. And the displacement here is 0, just meaning that whenever the signal is overlapped exactly on top of itself, well, then the correlation is 1. Same thing with the output autocorrelation, we're getting 1 with the displacement of 0. This is just kind of like a sanity check to make sure that at least, the algorithm that we're using, or the implementation of the algorithm is working. So then whenever we plug in the cross correlation and look at the output signal correlated to the input signal, we're seeing 0.99. So again, very good correlation for this WD 6000 antenna. And the displacement is off, which just means that we had to move this output signal down roughly, a quarter nanosecond in order to get it to line up. Moving on and looking at it with the packaging, we'll get, a little bit more variability here in the time domain signal of the red one. You can see some more ripples towards the end, and the cross correlation has dropped a little bit to 0.989. So again, still very good. And then whenever we look at the dual cavity antenna, clearly the output signal in this case is significantly different, and the cross correlation has dropped to 0.7718. So that was just another metric that we kind of came across as we were doing our investigation. With that, we will go ahead and wrap this up. Thank everybody for attending, and thank you for your feedback. Also a reminder that we recorded the session, and we'll be sending out a copy of the recording. We'll also be reaching out with you with a separate email, just asking you about some of your feedback and what you thought of the questions and of the antenna design metric in general. So thank you very much for your time, and I look forward to talking to you about this further. Enjoy the rest of your day.